And he earned his PhD degree from UTK, University of Tennessee, Knoxville, in 2016, and also an MBA degree from University of Colorado, Boulder. He has been, I think, with Yendral since then, isn't that right, Kumar?
Yes, since 2019.
Yes, yeah. So he is currently a senior research engineer at Power Systems Engineering Center in the National Renewable Energy Laboratory, Golden, Colorado. And he leads research projects targeting improvements in distribution system protection and interoperability of distribution system assets. He is a technical contributor in many microgrid controller evaluation projects and advanced distribution management systems evaluations projects. His research focuses on the hardware in the loop, power hardware in the loop, and remote hardware in the loop experiments. And he has collaborated with us on several proposals and projects, and he's really awesome to work with. Kumar,
Thank
please
you.
go ahead.
Yeah, thank you for that nice introduction. Um, I'm Kumar Guru Prabhakar. I'm a senior research engineer at Enroll. I guess it's been 8 years at Enroll because I'm getting old. But for today's presentation, I wanted to talk about uh, my sort of like day-to-day job and day-to-day role. Um, I I've worked with Anamika and Mani and all the professors from WSU on multiple proposals, and uh, this this presentation is sort of like where I try to contribute in those proposals, and I hope that through this presentation I can give some insights into how new technologies get integrated into the field and what are the steps that normally we take to move ideas from paper into an actual product and integrate into the system. Um, so we called it de-risking field deployment. The main reason being, if let's say you create a cell phone or any sort of software, if something goes wrong, depending on the size of the project, you may have some economic loss and other things. But if things does not work as anticipated in the field for power system, it can create blackouts, economic loss, life. We call it de-risking these field deployment of power system innovations. And we use multiple approaches, and I mainly work on the hardware in the loop experiments. So I'll discuss, all of those things. Just some background on Enroll. The building in the picture is our energy systems integration facility. The black box in the middle that houses our supercomputer, the high performance computing capabilities, and at the end, left side of the building is where we all run our experiments, and the right side of the building is our offices. And this is in Golden campus. And if you're in Denver or Golden, we do a lot of lab tours, so you can check with me and we can try to set up any sort of lab tour for our energy systems integration facility. And this is where we run most of our simulations, experiments, power hardware experiments, controller hardware experiments. Yeah. So just a brief background. I will present more in details, but we have megawatt scale controller and power hardware capability at energy systems integration facility. On the AC side, we can go up to 2 megawatts for controllable AC supplies. And in our Flatirons campus, which originally was called as Bin Center, we could go all the way up to 10 megawatts of controllable AC source. On the DC side, at ESIV, we have 1.5 megawatts of DC supplies, and I think higher power at the Flatirons campus. And we have RTDS, Opal RT, all types of digital real-time simulators that is out in the market. And we also build our own sort of software simulators to support these kind of experiments. And I work primarily on distribution side, microgrids, ADMS, microgrid controller, um, capacitor bank controllers, protection relays, and we work on all those equipment and try to run evaluation experiments, whatever that may be, from university side or utility side. So first, I wanted to start with the technology readiness level. And I think most of the professors know about these kind of terminologies. And I cited the original paper from 1995 here. And this is a technology. This is a metric that was built originally by the space industry. And from what I read in the papers, it seems like US has its own technology readiness level, and European Space Commission, they have their own readiness levels, and we're going beyond TRL 9 in some sense, and that's an R&D in management science, if I can call it that. So technology readiness level are metrics that are developed to assess the maturity of technology. Let's say, for example, WSU develops a technology, a new optimization or control, and another university develops that. How can you compare these two, or compare the maturity of these two? And the metrics are used to understand that. And this gives a way to compare, like apples to apples comparison between different technologies, so that utilities can make the right decision. So in the paper, they talk about 9 levels of maturity level, and it goes all the way from TRL 1 to 9. And initially, the early TRLs, we call like from TRL 1 to 5, they're very low cost, moderate or to moderate cost, and it's a proof of concept. So TRL 1 and 2 are like you're writing in a paper, use mathematical equations or physical limitations, and come up with a concept and say, oh, okay, this might work, this can solve, and those are low to TRLs. And then higher TRLs will be, or TRL 3, 4 might be like where you start to solve some equations in a software or do some simulations. And then when we go to higher TRLs, we go into much more details. And in the paper, again, the paper talks about this for space industry. So the ultimate idea is, let's say you develop new controls for a rocket or build new rockets. How can you evaluate the maturity of it before spending billions of dollars? Right, that's the idea, and other fields sort of hijacked that, and it's a very important terminology if we are proposing projects to DOE or utilities to convey where the state maturity of this technology is and what needs to be done to convert it from an idea to an actual product. So I copy pasted word by word from the paper because I feel like this is sort of like a definition for these kind of TRLs. So TRL 1, 2, and 3 are basic principles, like V equals to IR, those kind of things, and you use that to come up with a solution, come up with a product. And then TRL 3 can be your software simulation, like Simulink or OpenDSS, or EMT simulations like PSCAD, RSCAD, those kind of things. And then TRL 4 and 5 is where, or TRL 4 to 7 is where we sort of come in, like national labs or some universities have those capabilities now, and that can be DRTS, digital real-time simulators, and you run experiments with controller hardware in the loop, power hardware in the loop, and 5, 6, 7 can be actual power hardware experiments. I have some examples that showcase what this 5 to 7 mean, and then 8, you can say that it's almost close to maturity, and GE or ABB or Siemens, they have actual products. So when TRL 8 is like a really new product, and TRL 9 is what I think of it is uh, like 5 or 10 years worth of field deployment, like relays, protection schemes. Right now, microgrid controllers, advanced distribution management systems, they all can be considered as TRL 9. And you make some updates, you make some changes, but it exists in the field, and it has been successfully proven for many, many times. So next slide. So how people borrowed this for power system. So for us, for power system, what is proof of concept? What is breadboard validation in a lab environment mean? Now, what is breadboard for power system? What is a relevant environment? Like for space, if it's a lunar environment, you know about vacuum and heat and temperature, all those kinds are considered as relevant environment. What is that for us? And what is demonstration? What is considered as a demonstration versus a lab experiment, right? Um, for us, what we use is like boundaries of physics. We cannot uh, do things that violate physics, right? And then the next things are EMT simulations, dynamic simulations, and steady state simulations like PSCAD, RFSCAD, OpenDSS, GridLab-D, all those kind of simulations. To some extent, we can call that as a breadboard validation or a lab validation. And then we go into software, hardware experiments, and then hardware in the loop. Those can also be considered a breadboard validation or a lab environment. Um, and hardware and field deployment, you can consider both of them as demonstration again. But we all it all, I guess, depends on your goal behind these kind of de-risking, what the utility wants to do, and stuff like that. So I feel like for us, when we look at these kind of TRL, you have to consider the goal. You have to consider uh, all the scenarios that your technology might see in the field, and as long as you can emulate that, simulate that, you can consider those kind of things as relevant environment. Um, so for us, we have four major things, and this also is similar to automotive industry and other fields that have borrowed these kind of techniques. So the first one is pure simulation, and we used a microgrid controller example here, where how if someone comes up with a new microgrid controller technology, what are the approaches that we can use? And this can be expanded to ADMS, all sorts of controllers. The first step is, of course, pure simulation, whether it is in PSCAD, RSCAD, or OpenDSS, and then you try to show uh, the performance. And there are limitations, how long you can simulate, what type of events can you simulate, and what type of things can you emulate in the controls. For example, in pure simulation, we still don't have proper ways to simulate communications and cybersecurity, those kind of things. And it's a hard R&D topic. And there are many tools, but it's not commercially available. So we go into controller hardware in the loop where you're able to run the power system or other things in real-time simulation, and then you can exchange information between that and the controls. And that can be either through analog digital input output or analog input output, and or even actual communications like TCP/IP, PMU communications, DNP3, 67850. Those are all available in commercial. So those kind of actual interaction you can observe in CHIL, and which you're not still able to simulate completely in pure simulation. But there may be tools, but we don't have those commercial tools yet in our lab. And then the third one is controller hardware in the loop and power hardware in the loop. In this one, you're able to take some of the power hardware components outside and then simulate it with the power system. And this is where the megawatt scale controllable AC source and controllable DC source comes into play, because sorry, just add the pointer. Because then you can take the AC voltages from the model and amplify it in a controllable AC source and uh, use or make the power hardware think that it is actually in that system. For example, we can model the Washington State power system in DRTS and then assume that you're going to add a large PV plant, and you can bring those PV into the lab. Let's say, for example, 1.5 megawatt PV plant. We can bring it to our lab facility or any facility and then run experiments with it. And if you have the microgrid controls or diesel gen controls or cap bank controls, you can see how all of that interacts together. Right? The key difference between this and pure CHIL is sometimes you're not able to model the inverters or some sort of power hardware very accurately in EMT. So then this becomes a major advantage. Maybe the inverter manufacturer doesn't want to share their model. So then we can work with utilities, we can bring the same inverter, same firmware, and then run those for hardware in the loop. And the last one is hardware only. There are some times where we have to do hardware only. This is the most expensive experiment that anyone can run. And here we don't have any power system model or anything. It's actual assets, actual controllers, and actual inline voltage or actual power. And that has its own place for certain things. So first I want to use one of my projects as an example to see how we followed this blueprint, TRL, and moved the TRL from a low-level TRL to, I want to say, mid-level TRL right now. And this project targeted protection and distribution system, and there's high penetration of inverter assets. And I think when we presented this 4 or 5 years ago, this slide deck was had information, but now I think it's a cliched slide where everybody knows inverter-based assets. There's low fall current, bidirectional power flow, and protection. Some of the protection devices might not work under that paradigm. So we proposed traveling wave based protection or fault signatures to detect and locate faults because the traveling waves are very fast. They travel close to the speed of light. So if you can capture that, you're able to detect and locate the faults, and we are not dependent on the fault current contribution. So we avoid all the challenges with it and go from there. So the first thing we did, and almost everything in the slide deck I have are all in open source. Please let me know if you need any information, I can send it out. But the first step, this is sort of like the load TRL. We took the idea from the paper because from physics we know, yes, when there is a fault, it generates traveling wave. And if you can see it, you can backtrack using the speed of light and the network structure to detect it. So that was considered very low TRL level, and we ran software simulation, EMT. We used EMT PRV and showcased how this behaves in a transmission system and in a distribution system, and whether it actually exists and if we can see it. And you can consider this as a low TRL, like the TRL3 for location. And we showed, yes, as long as you can filter the high frequency waveforms, you can capture those traveling waves, and that has some information on location, and you can use that to detect and locate the fault. So then so this is a very simple model. It's not a relevant environment. It's not a breadboard, as to speak, for us. So we moved it to our breadboard, which is IEEE 13 bus system. Almost, I'm pretty sure most of you are aware of the IEEE bus systems, and 13 bus is a distribution system. We had to modify it a little bit and to make it a relevant system. For example, the 13 bus system does not tell you the tower structure or the cable structure, and that is pretty critical to model the lines for high frequency studies. So we had to assume a lot of things, and we modified the 13 bus system to make it very accurate. So this can be considered as a relevant environment. And these are the theoretical traveling wave time, 1.64 microsecond, and so on and so forth. Right? And then we ran simulations in EMT PRV, and we are able to see similar results from what we ran in just the 3-bus system. And now through this step, we are moving from 3 to, I want to say 4.55, some things like this. But again, this is still simulation. And simulations are just solving mathematical equations, right? So it is still very low TRL. So next step for us is usually digital real-time simulation. And when we tried to do this at the time, none of the RT or the DRTSs had the ability to model lines with high fidelity, specifically for shorter lines, because these models in DRTS can only run at 50 microsecond, and when you run 50 microsecond time step, you will miss all these traveling waves because some of them are 5 microsecond and shorter. So there was no actual way to do CHIL or PHIL. So we had to go to actual experiments. So we had to use power hardware experiments. So we had to use real world overhead lines and underground cables, use actual faults, actual bolted faults, use actual CTs, current transformers that can look at it and capture wide frequency data and show this in a field experiment. And we also had to show that we can differentiate between noise and the high frequency traveling waves. And if we could successfully do it, you can consider this like mid to high TRL. And this is going beyond breadboard and going closer towards what the paper called as space environment, right? So we had a facility, and this is a 20 kilovolt uh, facility, and you can run bolted folds. So you can see here we connected one of the phases to the ground, basically bolt through improper insulators, and then these green clamp-on CTs are what we use to capture those traveling waves, and the scopes are properly um, rated to around like 100 gigahertz or something like that, so you can capture them. And these are some of the locations where the underground cables, you could connect your CTs and look at what is happening inside the underground cables. So this setup is a mix between overhead line and underground cable, and this is the place where we used we added a bolted fault. Um, Again, more pictures showing how we ran all the experiments for a single phase fault. And this is sort of like the most expensive experiment that you can do. And I think there are some labs in Canada that does even more fancy experiments. And this cost close to $50,000 a week just for the human resource, power, all those kind of setup. But of course, there's a lot of initial investment that someone made to make this happen. So it can go more than millions of dollars. So we reserve these kind of experiments for things where you cannot model, you cannot simulate, those kind of things. And this is sort of like our theoretical calculation of how these traveling waves should travel in the overhead line and in the underground cable, and then reflect back. I kept the technical stuff very little, but we have very detailed information on these reports, so please feel free to take a look at it. And again, this traveling waves, they travel close to speed of light in overhead line, and 50 to 60% the speed of light in underground cable. Um, and then we looked at the results. So this is from the scope capture, and one half of this, or half of half cycle, is almost 15 microsecond. So you have to filter this out, and we used some novel techniques to extract this traveling wave from the raw waveform. So we basically did sort of like a subtraction. Um, so you can see the orange is the discarded waveform, and green is the denoised signal. So the green is the signal from that scope, and then we discarded orange. The way that we discarded that is based on the speed of light, and with the speed, the frequency, and then with the frequency, you're basically doing a high pass filter, and you're asking the signal processing to ignore everything low frequency and only consider that is high frequency, and then you can justify this as the traveling wave. And then we ran this with multiple experiments. Multiple times we applied the fault, and we used different types of CTs to make sure that it's not noise and it's not one-off. And basically, these are repeatable, reproducible experiments to um, um, increase the TRL to maybe 7 or 8. So this is sort of one of those projects where we went from low TRL to mid TRL using first software simulation and then skipping controller hardware in the loop and power hardware in the loop, and directly using power hardware approach. So this is another project where we used controller hardware in the loop, and this is for evaluating University of California, San Diego's microgrid controller, and you can also call this remote hardware in the loop. We ran the power system model using our ESIF digital real-time simulators, and this is a microgrid with a lot of DERs, 3 circuits, and a couple of diesel generators. We do have a 26 megawatt PV at the 69 kV substation bus. And the reason why I called it remote hardware in the loop, because this model was running in ESIF and the controller was actually running in UCSD. And we had a connection between NREL and University of California, San Diego through the generic internet IP, and then we exchanged information between NREL and UCSD using power system protocols. And if you think about it, this is how real world also works. The PMUs are in the field, the controller is in the utility control center, and they exchange information over either general IP internet or through dedicated connection. But the delays usually is like 120 millisecond is reasonable to assume that these delays are okay. So we sent PMU data from these PMU locations to UCSD, and then UCSD they make decisions based on that, and they run their optimization and send DER dispatch back to NREL's ESIF, and then we run this for different load profile, different PV profile to understand, okay, can this microgrid handle, or the controller, can it handle this microgrid? Okay. And on the right, we are showing the protocols. Basically, the C37118, which is the PMU protocol, goes to UCSD, and then the control commands come back to NREL in Modbus. When we ran this experiment, Modbus was standard approach. I think people moved to DNP3, and now they're trying to go to 61850 and other faster communications. So this is, and like I mentioned in the past, this is another advantage of CHIL, because this is the actual protocol that the UCSD controller will use, and this is the actual protocol it will use to send commands. And these are hard to simulate in software tools and understand how the delays will impact the control performance and so on and so forth. And these are some results from that experiment. Again, I'm not going into too much technical details on the performance of the controller because we don't certify or say yes, good or bad, those kind of things. We run experiments and we give the data back to the utility and the inverter manufacturer or the controller manufacturer, and then they can make necessary updates to their controllers and make sure that it'll perform better or meets the requirements of the utilities. And this is another project with the same microgrid, but we are using controller hardware and power hardware. If I go back here, we have this 26 megawatt PV and a battery energy storage system. So we basically took that and modeled that as an actual power hardware. So we had the same PV inverter in the lab with the same firmware that it's supposed to work in the field. And also a similar battery energy storage system that we could find at that time, and then ran power hardware in the loop. Like I mentioned earlier, we take the voltage from the point of common coupling and then scale it appropriately for the AC source, and then the inverter thinks that it is in that particular bus, and then it does its thing. Well, when we ran this project, it had volt-var control, volt-watt control, all sorts of advanced grid support functions, which are in the current domain, right? So we've just measured the current and fed it back to the model using a controllable current source, and then you close the loop. Of course, it's a little bit more complicated and complex than what I'm explaining here. And there are a series of papers that talk about accuracy and stability of these kind of experiments. The key point is we want to capture what the inverter will do in the field for a particular voltage event or frequency event. And we tried to mimic those events using the DRTS model. And we are relying on like these kind of decades old research that was done in the EMT domain that says, okay, if you do X, Y, and Z and model the system in EMT, then to some extent you can understand what the system will do. Um, so and the same thing with battery energy storage system. Of course, these inverters were grid following at the time when we ran this. I mean, I say at the time, it's only 3 years ago. We didn't have grid farming inverters, or it was not a key buzzword at the time. Right now, grid farming inverters, we are developing those kind of experimental science to run experiments with grid farming inverters so that you can replicate the model and you can replicate what the inverter will do in the system. Um, and again, the advantage of doing this is you don't need a black box model or software model for the inverter. You can just bring an inverter any day and run experiments, and it will be valid, with certain assumptions, I guess. And these are the results for that particular setup, and I just borrowed organization. So basically, the microgrid controller, it senses a lot of information from this setup, and it makes certain decisions, and either in dispatch or controlling when it should island, it should resynchronize those kind of decisions. And we ran those experiments, and everything looked stable, or at least for that microgrid controller. But again, we don't certify or say whether a controller is good or bad. We just run whatever experiment, and then we give the data back, and the controller manufacturer or the university will make the necessary updates to make it work. And we found so many bugs, and that's an advantage of this. Before pushing this into the field, we are able to understand why certain bug is there, and there were so many communication bugs. We fixed, we understood using the setup, and we fixed it before it can go into the field. And this constantly happens. For example, this the utility that we worked with, they have the DRTS model. They have actually like sort of like a digital twin of everything in their lab, and they constantly run experiments. They constantly try to understand why something happened in the field, how it can be mitigated, what can be a solution for that. And it's not widely used, but we are seeing that more and more people want to use it. And this will definitely push the TRL level into TRL 7 or 6. And this is what I sort of consider as our equivalent for space environment. Okay. So almost at the end of the presentation. So in summary, we presented some background on the technology readiness level, and I'm really hoping that students who are in this seminar can use the technology readiness level and use that when they communicate about the maturity of certain things, and hopefully that it's helpful in their work if they go into making new products, new type of things for a power system. And I presented background on software simulation, I think, which is pretty standard if you take any course. But I also presented the power hardware, controller hardware experiments, and power hardware in the loop experiments, which are bread and butter for my work. And we constantly try to improve accuracy, stability of these kind of power hardware in the loop experiments, so we can mimic the field events and make and de-risk these kind of deployment into the field. So that I am done with my presentation and take on any questions, comments.
Yeah, thank you very much, Kumar. There are two questions posted. I don't know if you can see the chat box, or I can read them to you. First question is from Dr. Surendra Bajagain. And this question is there a reason to have two PMUs at switch terminals? I think this refers to your 24, yeah.
Yeah, I think the PMU 2 and 1, it is needed because this can island, right, and synchronize back. So you need to understand the voltage on both the sides of the PCC. Um, I don't know if the controller uses that to make any sort of decision, but definitely those two PMUs will have different phasers if the switch is open.
And can you talk a little bit about that microgrid that you have here, the UCSD microgrid? Yeah.
Yep. This is from San Diego Gas and Electric, and it's their Rego Springs microgrid. I think we have all the information in the papers. I think I'm allowed to talk about it. And yeah, this is an actual microgrid, and it's not a university microgrid or a community center microgrid. This does have agricultural load, house loads. It doesn't have any industrial loads, but very residential and agricultural. And it is at the end of a long 69 kV transmission line. So there are reliability issues, and the line goes through wildfire area. So now it has resiliency issues. So this converting this distribution feeder into a microgrid increased the resiliency and reliability for this. And when they started, they used diesel gens as the grid farming asset, and the battery energy storage system and the PV, they were grid following assets to support some of the loads. But CEC, I don't think you can add new diesel gens or gas turbines as grid farming assets. So we have other projects where we are trying to use grid farming, battery energy storage system, grid farming, PV to support this in the absence of a diesel gen. So because if right now the diesel gen is working, but if it breaks down or something happens, uh, uh, they cannot add a new diesel generator. It has to be an inverter-based asset. So yeah, right now, or 2 years ago, we were running experiments and simulations to understand the performance of microgrid controls, but now we are using the same DRTS model, everything that was invested in setting this experiment to understand how we can run this microgrid using renewable grid forming assets. And to give a ballpark number, the total cost of all these projects around this microgrid is almost $10 to $15 million in total.
And what is the size of the microgrid?
The peak load is around 15 megawatts. So this has 26 megawatt PV and I think 6 megawatt of distributed PV, another 6 megawatt of concentrated PV, and yeah, I have to say it has 200% renewable energy, and there's definitely excess generation, and that adds to the challenge, right, of running this microgrid in a stable way.
Yeah, thank you. And the second question is, what open source tool would you recommend for the full simulator based approach?
Yeah, I think I would recommend OpenDSS or GridLabD. GridLabD. I always get confused between GridLabD and GridAppsD, but those are steady state, right? And the answer to that question really depends on the event. If your events are in steady state, like volt-var control, you're trying to understand dispatch, then steady state tools, simulation tools might be okay. But if you're thinking about protection, or lightning studies or traveling wave, those kind of events, you have to understand the time step. Let's say that if the event is in 1 microsecond, then at least for us, we do 10 times faster. So 1 microsecond, we may do 100 nanosecond time step. And the Nyquist criteria is, I think, twice, so 500 nanosecond time step. For that type of modeling, EMTP, ATP is the only open source tool. And I don't know, when I say this, it feels really old, but when I learned EMTP, ATP, they still used punch cards. I don't know if people know what punch cards are. It's a sheet of paper, you punch stuff in there, and then you feed it into a computer, and then the computer takes it in. and then run simulation and gives you another punch card, and then that becomes it. I didn't do actual punch cards, but EMTP ATP was still using those kind of punch cards, and you had to do that in Notepad and do those punch stuff and X's and O's to simulate that, and then you run that. That was the open source tool that I used in 2009, and since then they have improved it. They have improved their GUI. I don't think people would have to do punch cards anymore, but it's an open source tool, so it doesn't have um, the same GUI interface as other off-the-shelf tools. But since you guys are university, you should be able to use EMTP-RV. They give free license to universities, and PSCAD they offer, I think, a reduced price to universities. So those are the three software tools that we use for EMT, and of course there are other tools. I know Endrel is building EMT tool for high performance computing. These are all serial computation, so we don't have any parallel computation for EMT. And Endrel has some work on it. I don't know if it is open sourced yet, but if it is open sourced, I think that would be another tool that people can use. It's a long answer, but I hope I covered the different time domains.
Yeah, thank you, Kumar. In fact, we have license for many of the softwares that you mentioned, including PSCAD for the students and researchers working on these problems. Yeah, go ahead.
One other comment I want to make, and I think this might be also useful for the students. We are a user facility, and that is different from other national labs, meaning anybody can come to us and ask for capabilities, and most of the time we can provide them for free. Uh, and for example, the HPC, there is a yearly process where you can apply to EERE, Energy Efficiency and Renewable Energy Office, and they look at your proposal. It can be anyone, students, private companies, anyone, and you can use the HPC to solve. The key is to solve energy efficiency and renewable energy related problems, because we are a EERE lab, and we give preference or priorities to those problems. And the same can be said for the lab equipment. You can come to us and say you want to run a certain experiment or simulation or things like that, and there's a committee that looks at those proposals and decide how much money would be needed, mostly for our human resource and for electricity and stuff like that. And it's comparatively cheaper than other lab spaces. So beyond just the software, if you want to use any of our capabilities, you can check our website and you can reach out to me, and I can point to the right people if you want to use those facilities.
Yeah, that's good to know. I know PNNL has a similar facility for high performance computing. But I didn't know about the EERE mission that Endrel goes with. Yeah, thanks for the information, Kumar. And other questions from the room? Yeah, go ahead, Ali.
Yeah, let's say we have a model built in GridLab-D or OpenDSS. So what is the best way to convert that into an RTDS model? And then the second part of the question is, if you have a solution from OpenDSS and you have a solution from RTDS, so is there a difference between the two types of simulations? If you just look at it from the power flow solution perspective, like just ignore the hardware and then look at the network solution.
Yeah. So the answer to the first question is sort of like why I have my job security, because there is no direct tools. We have a couple of papers, and we have a couple of tools. I think there's a tool called Ditto that Endrel has that can convert between one to another. It can do multiple inputs, multiple outputs, but it comes with its own challenges, and it's not straightforward. And we almost all the time we have to manually do it. So I sit around like I know days where I just look at Excel all day long and copy paste, use some fancy macros in Excel to convert. And there are standards like CIM that tries to standardize this, and it becomes a problem of miles to kilometers, right? Where Europe uses a certain way and US uses a certain way, and there's no one solution that fits all. So you do have to do a lot of manual labor in converting it, and that's where your fundamental courses that you take in WSU comes to help, right? How will you model a line? What is a pi line? How can you model a transformer? How can you model a cap bank? What things do you need to consider? Those are all still not automated, and it is extremely challenging to automate that. But you can make some progress. So it's like a 50% automation, 50% manual. So you go from OpenDSS to some form of let's say pi line model, and then you copy paste from that. That makes life easier. Of course, RTDS has its own SIME to RTDS RSCAD converter. PSCAD has SIME to PSCAD converter. But again, this also because SIME is also a Canadian company or a Canadian product. PSCAD, RSCAD are Canadian products, so they are able to make that. But it's still a moving target, and there's no standard format for grid forming inverters. So, yeah. So long answer. The short answer is yes and no. You have to choose and do manual. The second question, like comparing OpenDSS and EMT, right? There was an IEEE working group that I think it was led by PNNL and other universities and other national labs. I don't think that working group exists anymore, but their goal was to sort of guide how you can compare, how you can run these kind of simulations and compare results. When utilities ask me that question, I always say it's sort of you're comparing, one. I don't want to call it imaginary. It's not imaginary. There is some scientific fundamental behind running these simulations, right? But you are comparing two imaginary solutions, right? The real thing would be to take field data. Let's say for this microgrid, you take the field data and you compare that field data to your simulation, and that is how you can get close to reality. And I always felt like comparing OpenDSS and RTDS would be like a random goose chase, and you would do a lot of work to compare that and make the models look alike. And then when you compare it to the reality, it will be something completely different. And it is also a moving target because there are utilities in US that do not know they're facing, right? They don't know which phase loads are connected to, and they have very little information on their distribution system. But that's also another job security for people like us, where you can try to get that data, and that's where some of the proposals that WSU has put in terms of AI and machine learning can bridge that gap, where you take the field data and then you use AI or machine learning to tune these parameters, line models, load models to match that. But you always have to do it every year because things might change. Like 10 years ago, things didn't change too much in distribution system. Right now, every 6 months, things are changing. So you have to constantly update that. So again, a long answer, but I hope that presents some clarity on the second question.
Yeah, thank you.
Other questions?
You mentioned that when you were doing like one simulation that the grid forming inverter were not available, so you use the grid following inverters. But from my experience, I actually feel the grid forming is more of like an older technology to grid following.
Yeah, I agree. I don't disagree with that. Droop control is sort of like one of the oldest control, right? Just diesel generators use it. A lot of inverters use it. I don't know, maybe, Mani, you can sort of explain why sudden fascination with grid forming inverters.
Yeah, this is a question maybe for class discussion. So, yeah, certainly, maybe Kumar, you can talk about your role in the big grid forming institute or the big grid forming center. Are you involved in that? And what are you working on?
So yeah, that's the Unify project. I forgot the full name for the Unify, but it is a consortium led by Enel. Dr. Benjamin Kropowski, he's the PI on the project, and it is funded by Solar Energy Technology Office. It's a pretty big project, $25 million, 3 to 5 years period of performance, and the ultimate goal is to sort of understand anything and everything related to grid forming inverters, interconnection standards like 1547, how should that update, and interoperability, like how the microgrid controllers or DADMS can talk to it and sense it, and yeah. So our role, I'm not an active project participant, but our role, our ESIF's role, is to leverage all our experimental capability, run experiments with it, evaluate the controls, and come to sort of present a report at the end of the project that people can use as their go-to document for grid forming assets. And another thing I didn't talk about in this presentation, I want to just briefly mention is the hydrogen, right? There is a big hydrogen push right now for all the right reasons, and we think hydrogen might overtake the lithium-ion battery energy storage system for long-duration energy storage, and that brings its own challenges. How can fuel cell support grid forming inverter? How can electrolyzer be used as a controllable load to take excess generation, convert electricity to hydrogen? And there's a whole bunch of research that needs to be done in the distribution system side, and all the approaches that I mentioned, we are hoping to use. This is in addition to Unify. Sorry, I just wanted to bring the connection between Unify and the hydrogen research.
So hydrogen, is it a new big initiative from NREL, or you are talking in general?
In general, I think in the bipartisan infrastructure law, there is a lot of funding that was allocated for hydrogen, right? And they are directly sort of skipping all this and going into field deployment. The scale is just, I've never seen. I mean, I've been only doing this in the last 10 years, so that is in really high scale of funding and a lot of research that needs to happen. A lot of human resource we need that can understand distribution system, and also how you can convert electricity to hydrogen and vice versa.
Yeah, that's an exciting initiative. WSU, we have a hydrogen sort of center called Charge that is pursuing the big hydrogen hub proposals.
Yep. Yeah.
I think the next round is, in fact, starting soon. So
yes, yeah, the hydrogen hub is pretty big, right? The minimum funding for that hydrogen hub is like $400 million or something like that. So it is beyond my pay scale, I guess, beyond a lot of people's pay scale. Yeah.
Yeah, Washington State has joined together with Oregon, and together we are trying to seek one of the regional hubs. We will see how that plays out, because, as you know, when state governments are involved, there is a lot of uncertainty into how these develop. And so we will see. Other questions from the students? If not, thank you so much, Kumar. It's we learned a lot about the technical readiness levels and also about the hardware in the loop simulation and experiments. Thank you very much, and we look forward to continuing our collaborations with your team.
Yes, yeah, likewise, and thanks for the opportunity. I'm
Yeah,
glad
thank
to-
you very much.
Thank you.
Okay, thank you all very much and see you next week. I don't know who is the speaker next week, but you will be hearing from Jenny